Hello guys, I hope you're all fine. Today I am going to discuss and show you that how a refrigeration loop can be simulated in Pro 2 process engineering. I just changed the background of Aveva Pro 2 process simulation and it is very easy to do it. All you need to do is to go to the options and change it to what color you like the most, like white. If you want to change it into white, then it's look like this. I prefer black for me. And now in this task we are going to perform simulation. um, the description is defined in this file here, that our refrigeration loop was originally designed to take advantage of a low temperature stream from another process to help condense the refrigerant. Now it is proposed that some or all of this stream will be used elsewhere in the plant. Elsewhere in the plant, you must determine the effect on the refrigeration loop of losing this auxiliary cooling duty. So what we need to do in this task is to check that if the auxiliary cooling is used elsewhere at the plant, then how much effect will be observed in the refrigeration loop. So we will do this by setting up a recycle loop of a small circuit which consists of a subcooler, then a let down valve, then it goes to the separator from where the liquid and the vapor is separated, and then liquid is goes to the evaporator, and then the vapor stream and the evaporator outlet combine and via mixer, and then it goes to the compressor. uh, this is the process flow diagram of this circuit, as I have already explained, that the separator and then this evaporator outlet stream then mix with the separator overhead, then it goes to the compressor. In this compressor we will use the curve data available in this file, and then it goes to the condenser and then move again to subcool exchanger. So the gas composition is given here, like ethane, propane, ibutane, and butane is used as a refrigerant in this simulation. Because the process will change the flow rate through the existing compressor, so performance curve supplied by the manufacturer are used in these calculations. We want to study that if there is a change in process, then the gas flow rate will also be changed. So for that reason we are using the performance curve in the compressor. Okay, so the thermodynamic package is Pang Robinson, and for the liquid density uh, we are going to select the leak gas flow correlation. Okay, so the independent variable is the flow rate of the refrigerant, so it's the independent variable and not dependent to any other variable like temperature, pressure. This flow rate is estimated This flow rate is estimated for stream 1 based on the latent heat of propane. Okay, so a feedback controller is used to calculate the vaporizer exit stream, and this exit stream is set at dew point, and this adjust controller which act as a feedback controller uh, adjusted the heat duty of this evaporator by changing this um, refrigerant flow rate. Okay, so there's a lot of theory here in this file, and let us read it first to clear the objective of this simulation. Okay, so that there are two ways to sequence a controller related to the cycle. Okay, so the other way is to sequence the controller after the last unit operation the cycle loop. So we will use this method, and we will first generate a cycle loop and then add all the process equipments and then use the adjust or feedback controller. Okay, what we want to study is here we want to study the fact of reducing the duty of subcool using Aveva. Okay, so we will provide the duty to subcool heat exchanger, and we will reduce it to check the effect on the refrigerant flow rate. Okay, so it will take too much time to understand all of this material here and the screenshots, so we will perform the simulation quickly and achieve the desired results, and then we will manipulate the subcooler heat duty and analyze the change in flow rate and the effect on the compressor duty. So let's see. Who is watching it live? Because I was planning to perform this tutorial or simulation yesterday, but I did not get it some time, so I was really busy, so I'm doing it right now. Thank you for watching my recent videos, my recent two videos which were done on the same software Viva Pro 2 Process Engineering. Okay, so let's start the game. The first step is to add the components from the given component list. So what we need to add is ethane, propane, C3, isobutane, isomer of butane, and normal butane. So our component list is completed. So the second step is to select the thermodynamic package. And this simulation there is hydrocarbon involved, and our operating pressure is also less than 100 bar, so we are selecting Bang Robinson. For the stability we are going to select leak Kessler as liquid density and is also mentioned in the tutorial. So right now we are following the tutorial, and for the sake of the data given in the PDF, in order to achieve the same results, we are following the same written description. Okay, so the thermodynamic package is ready. We are going to add the first stream here, which is called S1. Fluoride composition. So we have individual component flow rates given in the PDF. Okay, so we have ethane 1.04, propane amount is larger than other components, 96.94, and is the significant one, 1.68 isobutane, and the least one is 0.34. So we also have to add flow rate as assumed 20,000. Alright, so we are going to select the temperature as 140 F and pressure 315 psi. So our stream is ready. So we will move it into 180 degree. Okay, where's okay, here's the option, rotate to 180 degree. Now we will add heat exchanger, another heat exchanger, another heat exchanger. This one is subcool. This one is a condenser. This one is the evaporator. Okay, we have developed the simulation model, but the data entering process is still remaining. So first we will add the recycle inputs, and we also have to generate a recycle loop. Okay, so there is the option of calculation sequence. In this tab you will find different options of sequence method, and we are going to select this, um, which is you can say a manual based calculation sequence, in which we can move the equipment in the loop from first to second or second to third, but it depends on the conditions and the requirement. So now we have added the cycle loop. The process data is also required to change here, some tolerance limits. Okay, so our loop will start from subcooled and end at condenser. This condition is from minus, so we will reduce it to 0 for the as an acceleration parameter. Okay, global recycle stream tolerances, so it's relative, so we can also change it as we like. So let's not change it right now and click OK. Okay, so let's start entering the data from, we have already entered the stream 1 data, now from the subcooled. Okay, so pressure drop um, for the subcooled is 5 psi, and specification is duty, in our case 17.68. Okay, so we'll select the outer pressure to 83 psi. Separator parameter 0, and is by default, there is no need, because the product phases is already defined, like the 4 stream, all the vapor um, will be received in the 4 stream product, and the liquid in the 5. Okay, so evaporator code 9, specification is cold per liquid fraction, which is 0 at dew point. Okay, so mixture outlet pressure is around 70 psi. Okay, so now here's the compressor. So calculation method is GPS engineering data book and actual head curve, and we have also single adiabatic efficiency curve. So let's copy paste the data from here. First one is with the head. See, it's very easy to copy paste the data from the Excel file. Okay, so next data is efficiency. So what we will do is remove this from here and add this efficiency curve from here. This curve is given in this file, and all the data or process data which I've already entered in the circuit is also already is also given in the file. So I'm not adding any data by myself or my okay. So this is compressor. The last one, condenser. 8 psi. One. Okay, so let's try to run this simulation without adding any control. Oh wow, it's converged. So our first phase has been completed. So the base case is ready as it is. Where? Okay. So what will we add here for analyzing the process data? Material balance and all. Okay, so we have this stream here, and we can also add this unit properties. So we can add a property table here for a quick view of duty spec. Select heat exchangers. Okay, so we have 3 exchangers. We will add all, and now we have duty here and the table here. So the first phase is completed. Now we will add a control loop, a feedback controller. Here is the controller. Parameter is heat exchanger, evaporator, duty. Duty is set as 82.72 and its tolerance is given as absolute tolerance of 0.001. Parameter stream, one stream, and flow rate. Right. Okay. Now what we need to do is to add this controller adjust in the calculation sequence. F1 is the evaporator. Make sure this adjust controller uh, covers your control loop, like starting from subcooled, it goes to light down, then separator, then evaporator, and at the evaporator outlet, uh, it will adjust uh, the stream 1 flow rate which is entering into the subcooled by changing the flow rate based on the evaporator duty and the dew point of the outlet stream. So the control loop is organized automatically. Okay, so let's run it. Okay, so as you have seen that the controller runs the control loop first and then it ends up at the cycle loop as given in this calculation sequence. Okay, so our model is ready and now we will have to analyze as we mentioned at the beginning of this workshop. So we have completed all these steps already. So our model is looking like this. Here it is. So at subcool duty of 17.34, stream 1 flow rate is this, and for example the auxiliary cooling media is used at other plant of at any other plant as mentioned in this file, then reducing this subcool duty will result in increase in flow rate and increase in compressor horsepower, condenser duty. So let's see what our model is showing. So our flow rate is 18. It's almost the same as it is given because we entered 17.68. So if we change this to 17.38, run. It's 18875 and 18899, almost same. Okay, now as it is mentioned here and in the beginning, propose that some or all of the stream will be used elsewhere in the plant. Okay, so the subcool duty should be reduced if we want to analyze it, and in return it should increase the flow rate of this stream. refrigerant. Okay, so we are going to reduce it to 15. As you can see that the flow rate is increasing when we reduce the duty of subcooler. 20,000. Okay, we can also generate reports in the Excel sheet as it is shown here. Okay, so what's the conclusion here? The plant can operate at a reduced subcooler duty at the cost of additional compressor power requirement due to increased refrigerant circulation. Okay, it is obviously that if there is an increase in flow rate, then the compressor duty will also be increased. The land and equipment charging will need to be validated at that rate. Okay, so hydraulics point is also included here. So we need to initiate a plant change for that. This simulation shows that the importance of considering the real performing gaseous process equipment. If the compressor were specified with only a defined exit pressure, the problem with increased flow rate might not have been detected until later and more costly stage. This is the most important point here. That if uh, we do not enter the real performance characteristic of the compressor, then we will not analyze it that there is a change in flow rate, because we put a fixed flow rate in the loop and we don't understand that what is happening at the backstage. Okay, so here is our simulation. Let's again change it to what we have in the start. Run it. Okay, it's not working here. I don't have this license same for me, so I can only generate tax report and Excel reports as shown in the material balance grid. Okay, so I hope you like this tutorial and understand that what I am trying to explain here in this video. Thank you for watching this video, and subscribe my channel and stay tuned for the next tutorial. And if you want to learn this software, I am also providing training um, on weekends through the Zoom, so I can provide a one-to-one training to you on this software. You can write me an email on engg.shazib@gmail.com, or you can also message me on LinkedIn or Facebook. So thank you very much for watching this tutorial.